We've been talking about games, and in particular the idea of Nash equilibrium, and we've looked at some examples of games which have one or even multiple Nash equilibria. Now we want to switch to slightly more complicated settings where we're going to look at games that actually don't have a Nash equilibrium, at least not in the very simple strategies we've considered so far. We're going to have to generalize the notion of a strategy to do this, and let's start with a simple story where you can see where this generalization comes from. We'll think about penalty kicks in soccer, where in a very simple version of penalty kicks, the kicker has to kick left or right, and the goalie has to anticipate left or right and jump to defend either left or right. Let's ask about what the payoffs are going to be and what strategies we would expect to see used. Well, clearly, if the kicker is going to kick right and the goalie knows it, the goalie's going to defend right. And that's not good for the kicker because the kicker is likely to lose and not score the penalty point. So having both of them choose right couldn't be a Nash equilibrium. Having both of them choose left also could not be a Nash equilibrium because the kicker would want to kick right if the goalie was going to defend left. What's really going on here is that both the kicker and the goalie need to be unpredictable. That's a phenomenon that you see in lots of different games. You somehow have to randomize so that your opponent can't predict exactly what you're going to do. And that's what we're going to look at next. How do you think about randomization in games? How does that change what the payoffs are? And then how does that change what we want to think about with the Nash equilibrium? So to do this, let's take that idea of penalty kicks in soccer and actually set it up as a game. We'll make player 1 the kicker. He chooses rows. Player 2 the goalie. He chooses columns. And the payoffs in this matrix represent the probability of each of them winning. Remember, the first entry in each cell is the kicker's payoff. The second entry is the goalie's payoff. So, for example, if they both go left or both go right, the payoffs are half each. They're equally likely to win or lose. It's just random. Whereas alternatively, if the kicker kicks right and the goalie defends left, then the kicker wins all the time. And if the kicker kicks left and the goalie defends right, here we have the kicker kicking 3/4 of the time. Perhaps what's going on is that this is a kicker who's better at kicking to the right than he is to the left. And that's why we get these slightly asymmetric payoffs. In this game, just as we discussed a minute ago, there is no Nash equilibrium, at least in these strategies of simply going left or right. And to see that, let's quickly run through this matrix. Start, for example, with the idea that they're both going to go left. That can't be a Nash equilibrium because if the goalie's going to defend left, the kicker wants to kick right. So we would move to right for the goalie and left for the kicker. Of course, if you do that, you'll see that that's also not a Nash equilibrium. In fact, for any pair of strategies in this game, one of the players is going to want to move somewhere else. So you can imagine circling around in this game. Nothing is stable here. There's no Nash equilibrium. To find a Nash equilibrium, we need to introduce the idea of being unpredictable. And we're going to do that with the idea of saying that the kicker kicks left with probability P. And the goalie defends left with probability Q. So if the kicker's kicking left with probability P, of course he's kicking right with probability 1 minus P. The goalie defending left with probability Q makes him defend right with probability 1 minus Q. We've now generalized the notion of strategies. Strategies here are simply P and Q, rather than simply going left or right. The idea of a Nash equilibrium is exactly the same, however. A pair of strategies, now P and Q, that are best responses to each other is a Nash equilibrium. We know a little bit in this game about what's not a Nash equilibrium already. We know there can't be a Nash equilibrium with P or Q equal to 0 or 1, because that involves somebody being completely predictable, and that we already saw isn't a Nash equilibrium. So now we have a game with two players, strategies P and Q. The only other thing we need to do to really analyze this game is to figure out what the payoffs are. The payoffs now are slightly more complicated because of that randomness. They're not just the entries in this payoff matrix, but we can figure them out from what we have in the payoff matrix. Let's think first about the kicker. If the kicker chooses to go left, then with probability Q, the goalie's defending left, and the kicker wins half the time. And with probability 1 minus Q, the goalie's defending right, and the kicker gets payoff 3/4. Right? So the kicker's payoff from kicking left is 1/2 Q plus 3/4 1 minus Q. And similarly, if he kicks right, his payoff is 1 Q plus 1/2 1 minus Q. We've got the kicker's payoffs now from left and right using the goalie's probabilities of defending left and right. And we can do exactly the same sort of thing for the goalie. The only difference is now the goalie has to say, what's the kicker going to do? Well, he's going to kick left with probability P and right with probability 1 minus P. So for example, if the goalie defends left with probability P, the kicker's kicking left, and the goalie's payoff is a half. With probability 1 minus P, the kicker's kicking right, and the goalie loses, he gets a payoff of 0. And we can compute the same sort of thing for the goalie going right. Now we really do have a game. We've got two players, their strategies P and Q, and at least some notion of what their payoffs are going to be in terms of computing these expectations of the payoffs in the matrix using P and Q. All we need to do now is to figure out how to find a Nash equilibrium in these more complex strategies, and that's going to be our next topic.